Hello and welcome to the lecture of the third task of Cloud Systems Engineering. In this task, we will talk about making distributed key value store of task 2 fault tolerant through replication. But before we get more into detail about replication and this week's task, let's talk again about why we actually want to distribute a single node key value store in the first place. As we saw in last week's task, one reason behind it is performance. So instead of letting all the requests go through only one server, which limits the throughput to the throughput of this server, we distribute the key value store across multiple shards, so that we basically scale our system linearly with the amount of shard servers in our system. The second reason behind distributing a single node key value store was fault tolerance, meaning that if a single node key value store would fail, all key value pairs are lost. And this, of course, also holds true for a sharded key value store that we saw in task 2, since if one shard fails, every key value pair of the partitions that are stored on this shard would be also lost. So in this task, we want to combine both and build a sharded key value store which will give us the performance and scalability, combined with the replication, which will make the entire system fault tolerant. So to summarize, in this week's task, we will learn about how we can make our existing distributed key value store fault tolerant through replication. We will learn about the basics of the raft consensus algorithm, which is the basis for the replication which we will do in this task. And lastly, we will build our own distributed and replicated key value store by using the raft algorithm and building on top of the sharding in task 2. So let's start with a bit of background information about replication and the raft consensus algorithm. And in particular, we want to focus first on the challenge that we have to overcome when replicating data onto multiple servers. So let's take this as an example where we have a replicated key value storage with 3 servers called replicas. And we want to essentially replicate the entire key value store onto these 3 servers, so that ideally, if 2 replicas fail completely, we can still recover the entire key value store from the last replica. Now we have overall 3 different challenges that we need to tackle when our 2 clients work on this distributed and replicated key value store. The first challenge that we need to tackle is we need to somehow handle the case where clients want to make updates to the same key on different replicas, resulting, of course, in a state conflict between the 2 replicas. So here the challenge will be, how can we decide on a consistent value here for the key X between the 2 replicas? Secondly, we also need to take care of server and disk failures, of course. So how should the system react if a server does not respond anymore or a disk of a replica gets completely broken? And subsequently, also, we should tackle the challenge if a replica comes back to life after a certain amount of time, after a few minutes, for example. How then should the replica be informed about the updates that have been made in the meantime when the replica was down? And lastly, we also tackle the challenge. We should also tackle the challenge of how should we react if the network fails or a network partition happens between replicas. And as follows, there's no updating between the replicas anymore. One rightly known type of replication that aims to solve these issues is the leader-based replication protocols. Here we have a single leader server, which is responsible for communicating with the client, determining the exact order of the operations so that there is no conflicts between operations. And it is also responsible for orchestrating the replication onto the follower nodes. The follower nodes are basically just copying what the leader does and cannot communicate with the clients themselves. The followers are then also involved in a so-called leader election, which determines which server is the leader node of this replicated key value store. This is essentially useful for when the leader fails. Then the remaining followers, of course, need to negotiate a new leader for handling all the requests from the client, which is done by a leader election algorithm, which results in a new leader at some point, which takes on the leadership of the replicated key value store and continues to serve the requests from the clients. Over the years, many different leader-based replication protocols have been developed, such as prominent ones as Paxos or Zap. However, in this task, we will focus on one of the easiest and also one of the most recently developed protocols, which is the Raft algorithm. So here you can see a rough overview of the Raft algorithm. On the right, you can see different Raft servers that are communicating with the client. And we have one leader and multiple followers, which all consist of three different components that make the Raft algorithm work: the consensus module, the log, and the state machine. The consensus module is responsible for the core logic of the Raft algorithm, including both the log replication and the leader election. The log is simply a persistent chain of all operations that have been made on the key value store, so that if we would apply all these operations in a particular order, we would obtain the state of our key value store. And lastly, the state machine is essentially the state we want to replicate. So in our case, that would be the key value store, which results in applying all the operations that are stored on the log. In the following, we will now go over a bit on the two main parts of the algorithm, including a normal operation of replicating a put operation and how we can actually elect a leader if the leader fails. So here you can see a normal Raft operation where we have one client and the replicas consisting of the leader and two followers. Each of the replicas is maintaining a log of all the operations that have been done on the system so far. And they also store until when the operations are committed yet, which is denoted as the green arrow. Committed here means that the operation, every committed operation is replicated successfully on the entire system and applied to the state machine. So when a client then sends a put request to the leader will then append this operation, the put operation, to its log, but not commit the entry yet. Then the leader will send an append entry request to all its followers, also specifying that every entry has been committed before this operation. The followers will then append this operation to the log and commit every operation before this operation. If they have successfully committed, if they have successfully appended this operation, they will then send acknowledgement to the leader again, which can then commit this operation and send an acknowledgement back to the client, which then knows that this operation has been successfully replicated in this Raft setting. So now let's talk a bit about the leader election in the Raft. So in a normal Raft setting, the leader will send messages regularly to the followers, even if no operation is happening at the moment, which lets the followers know that the leader is still alive. This message is also known as the heartbeat of the leader. Each node also holds a specific term number, M, which specifies the number of terms so far where different leaders had the lead of this replication, of this Raft replication. This is important for the leader election later. So now, if the leader has not sent a heartbeat to the followers in a specific time interval, the followers will detect this and assume that the leader is not working anymore. The first follower to detect this will then become a so-called candidate, and it will try to become the leader now by increasing the its term number, and sending a request vote message to all remaining followers. Those remaining followers will then also notice that the old leader is not working anymore, and also increase the term number and send a vote for the new candidate, which then, if it got the majority of votes, will become the new leader of this cluster. So yeah, if you want to have a bit more insight into this leader election, I would suggest you to check out the official website of Raft, which I can show you the link later, where you can have a interactive visualization of the Raft algorithm, where, for example, here a Raft election is taking place, and we have a leader, and we can actually also kill this leader, so it's not working anymore, and then we can see how a new leader is elected by the cluster. All right. So now, finally, coming back now to the problem we had initially, how we can actually combine both sharding and replication. So of course, in task 2, we built our sharded and therefore scalable key value store. However, we still had the problem of that if one node fails, we lose every partition of the respective shard. However, we can simply combine now the two concepts of sharding and replication by distributing each shard across the different server nodes, where each shard has now a leader node and multiple follower nodes that are on the on the other nodes. And we do it in a way that the leader is always on the node, on one node, and the followers are on the other nodes, as you can see here for each shard. So if now a shard or a node fails in our cluster, we simply elect a new leader for the shard where the leader has been on this respective node that failed. And every shard can now still be served from the remaining two nodes by not losing any data of the system. So yeah, if you want to keep on reading about the Raft algorithm, I would recommend you the lectures from Martin Kleppmann on consensus and the Raft algorithm, which are lectures 6.1 and 6.2. Here's the link for these lectures on YouTube. The Raft consensus algorithm on the Raft website, which I just showed you. And if you want to go really deep into the topic, you can also have a look at the paper itself, which introduced the Raft algorithm in 2014.